Okay, Math 1630 students, this is our last lesson, the one you've been looking for all year long, and it is about logarithmic functions. So the definition of a logarithm says simply that if you have a logarithm to base a, and notice here that the base in the logarithm is the same as the base of an exponential expression, that if you have a logarithm to that base, the logarithm answers the question, what power can you raise a to that will give you the value of x? And notice that y is the power. So notice the location of x and y. Essentially, what you're going to do when you're evaluating a logarithm or trying to convert from log expressions into exponential expressions is you're going to take the base of the logarithm in this case the base is a, and you're going to raise it to the y power and the result is going to give you the value of a raised to that power, and the result actually moves to the other side of the equal sign. It swaps places, so to speak, between x and y. So some numerical examples of this. We have 3 squared is equal to 9. Notice that the base is 3. And that when we square 3, the result is 9. So 3 to the second power is equal to 9. So drop the base down as the base of the logarithm and then swap places with x and y, and you have the equivalent expression. 1/5 to the negative 2 power translates to a 1/5 base logarithm, saying that 1/5 raised to the negative 2 power gives us 25. The same thing works with all of these. 10 raised to the 5th power. 10 is the base. The power is 5. And the result is 100,000. Again, 4 is the base. 1/64 is the power, and the result, 1/64 is not the power. Let's back that up there. The base is 4. The power is negative 3. And the result is 1/64. So the result is what you're actually taking the base 4 logarithm of to get the power. There is a special case here, and that special case is the very last one. E raised to the 0 power is 1. Now, of course, E isn't the only thing raised to the 0 power that's 1. anything to the 0 power is 1. But in particular, e is an interesting number, and it'll lead us to talking about something called the natural logarithm somewhere in this section. So take into account that e to the 0 power is equal to 1 tells us, just like it does with all the others, that if e is the base and 1 is the power, 0 is the power, then the result is going to be 1. And oftentimes we will see this logarithm written rather than as log base e. We'll almost always see this written as ln 1 equals 0, because base e logarithms are written as ln. And of course, e can be raised to other powers, but in order to avoid writing the base, when we have a natural log, we're just going to call it the natural log. If you see simply log to some base of a number, only the base actually isn't there, then you can assume that this is base 10. If you see ln, you can assume that that is a log base e. Those are the two most commonly encountered forms, and these are called common logarithms if they're a base 10, and then natural logarithms if they're a base e, and that's mostly what we'll use. A logarithmic expression is actually a function because there's only going to be one power that you can raise the base a to get the result of x. Some key things to pay attention to is that your x has to be positive. The result has to be positive. The result, once you take a to the f of x power, the result of that has to be a positive number. Otherwise, the logarithm is not a logarithm. It's not actually a feasible statement. This is an example of why logarithmic functions are inverses of each other. 2 to the x power is the inverse of log base 2 of x. The definition of an inverse is when you interchange x and y and then resolve for y, the new expression is the inverse of the original expression. And in this particular case, the inverse is actually a reflection of one function for the other over the line y equals x. If you folded this graph along this blue line, y equals x, then this curve matches this curve. They are mirror images of one another. Now, these are properties of logarithms. And these properties actually come from properties that, if you think back, you've actually seen these properties before. Remember the exponent rule. says that if you have some number, and I'm going to in this case use powers of 2. If you have 2 to the second power times 2 to the third power, that turns out to be 2 to the fifth power, because this is 2 times 2 times 2 times 2 times 2, and that gives us 2 to the fifth. So we add the exponents. For that reason, because of the exponent rule that says you add the exponents, then you can add the logarithm if you can break what you're taking the log of down into 2 separate factors. Similarly, the second property, log of x over y, is equal to the difference between the two logs. That's because if you have 2 to the third over 2 to the second, that turns out to be 2 to the 3 minus 2, or 2 to the first. And thus we have the subtraction. The third one, option C, says that if you have 2 to the second power raised to the third power, if you remember what you did before, that meant you had 2 squared times 2 squared times 2 squared, which is 2 to the 6th, and 2 times 3 is 6. And so, similarly, if you've got what you're taking the log of is something to a power, you can actually bring that power down in front and multiply by it, just because because in the exponential expression you're multiplying your powers. D says that a to the first is a. We know that's true because anything raised to the first power is the same as itself. So if the base and what you're taking the log of are identical, then the result is going to be 1. This one goes back to what I said last time. A to the 0 power, like e to the 0 power, is equal to 1. Anything to the 0 power is 1. So any base logarithm of 1 is going to be 0, because 0 is the only thing you can raise that base to that you'll get the result of 1. And then this one, of course, is kind of like a useless restatement in some ways, because this says if you take the base a, oops, needed a highlighter. If you take the base a down here and you raise it to the r power, well, guess what you get? A to the r power. So we're going to solve some logarithmic equations. And the first one that we have here is 3 raised to what power gives you 5. Now ordinarily, if this were a problem where 3 was a factor of 5, that would be actually fairly easy to solve. But 3 is not a factor of 5. So what we're going to do is we're going to make use of some of the properties by, first of all, we're going to take the natural log of both sides of this equation. The natural log of 3 to the x is equal to the natural log of 5. And I want you to keep in mind that the natural log of 5 is a number. You can get a decimal approximation of it on your calculator, so that is just simply a number. On the other side, we're going to use the property that the natural log of this to a power, we can bring the power down in front and multiply it by what's left, which is, of course, the natural log of a. In this case, 3. And then keep in mind, just as the natural log of 5 was a number, the natural log of 3 is also a number. And so in order to remove the natural log of 3 from the x to solve the equation, we can simply divide by the natural log of 3. And the natural log of 3 cancels on this side and gives us a solution to the problem. X is equal to the natural log of 5 over the natural log of 3. And keep in mind, these are just numbers. You can actually calculate those numbers to a decimal and get a decimal approximation for x. Now this one's actually, okay, here we have a slightly more complicated situation. In this situation, we have two different bases to two different powers, but we're still going to apply the same principle. We're going to take the natural log of both sides. And then we're going to use the same rule we used in the last case to bring the power down in front of the logarithm. So that what we have remaining is the natural log of 3 and the natural log of 4. And I want you to remember that the natural log of 3 and the natural log of 4 are just numbers. In fact, the natural log of 3 is actually approximately 1.0986, and the natural log of 4 is approximately 1.3863. So please notice that I'm not dividing by that. I'm actually saying that that's the same thing. So just keep in mind, those are numbers. They're not variables. You only have one variable here, and that is x. Now, I'm going to make another little swap that involves the 2. I'm going to combine the 2 with the natural log of 3. So what I have there is actually going to be two times the natural log of 3, and again, that's just a number. And it's about 2.1972. And what we have left then is just the x. And that's equal to, now on the other side, we're going to break the x plus 1 apart. We're basically going to distribute that. We're going to multiply the natural log of 4 times each of these two terms. Essentially, just to make it easier for you to visualize this, essentially what we're going to do is we're going to take the natural log of 4 and we're going to multiply it times x plus 1 using the distributive property, which means that what we're going to get is the natural log of 4 times x and then we're going to add that to the natural log of 4 times 1. Because remember, this is just a number. So we're basically distributing a number across both of these terms. And again, the value of that number is simply 1.3863. And since this actually is a number times a number, then this actually is the same thing, 1.3863 times 1. So this whole value is going to be 1.3863. So at this point, what we need to do, since this is a number, and we've got an x on each side, we're going to subtract the natural log of 4 times x from both sides. So that what we have now, taking the 2 times the natural log of 3 times x is still out front. We have two numbers in front of x. And on this side, this term is gone, and all we have left is the natural log of 4. So now we have x in both of these terms, and we're going to factor that out. So we have x times two ln 3 minus ln 4. And that, of course, is equal to ln 4 on the other side. So our final step is going to be to solve for x. And when we solve for x, since this is multiplied times x, we're going to divide both sides by that number. Because remember, this is not variables, this is just logarithms, which means it's just numbers. So as usually happens, on the left-hand side, the factor that we divided out cancels, and we're left with simply x. And now we have that x is equal to the natural log of 4 divided by 2 times the natural log of 3 minus the natural log of 4. And once again, this is simply a number. And we have a value for x. If you want to evaluate it on your calculator, all you do is begin by taking the natural log of 4 and dividing it by the sum of 2 times the natural log of 3 or I'm sorry, not the sum, the difference, so we're subtracting the natural log of 4. And the decimal is about 1.7095 if you want to check that on your calculator. But this is actually the solution that we're looking for. I'm only trying to emphasize to you that that the result here is just a number. It's just an odd looking number. So for our next example, we're going to employ this trick one more time. Only this one's a little simpler, because what we have here is a number times e raised to some power, where x is in the power, and it's equal to 9. And in this case, we don't need immediately to do the natural log. We need to isolate the term that has the x in it on one side. So the first thing that we're going to do is we're going to divide both sides by 5. And that leads us to e to the 0.01 power is equal to 9 over 5. And since that's a nice decimal number, we're going to go ahead and call that 1.8. And then, since we're trying to find the power, what we're going to do is take the natural log of both sides. And then again, we're going to use that power rule to bring the 0.01 down front. And I've inconveniently left out my x's, so let me go put those back in. So this is 0.01x times the natural log of e. And remember that the natural log of e to any power, and in this case that power is 1, is actually just 1. So what we actually have then, since ln e is 1, is 0.01x is equal to the natural log of 1.8. And then dividing both sides by the 0.01, to get rid of it in front of the x, we come to the conclusion that x is equal to this expression, which is about 58.799. This is called a change of base theorem for exponentials. And we're only going to do one example of it because it's not something that we're going to need to do a lot of, because we're not going to solve a lot of equations that are not base e or natural logs. But if you want to write 7x using a base e rather than base 7, then basically the function of 7 is that it's the value of a. And if you want to write it to base e, what you actually do is you take the natural log of a, and it becomes the power on e. It becomes part of the power on e. And then we retain our x as part of that power. So if you have a base raised to the x power and you want to write it as a base e logarithm, or an exponential with base e rather than base a, then all you need to do is add the natural logarithm of whatever the base is to the power on the e. So this concludes our lesson on logarithms. You should be ready to try some of your homework problems. And if you have any questions, just let me know.